Hello everybody, and welcome to our video addressing the physics principles of angular acceleration and how it relates to net torque. In this video, we will explain concepts related to these principles, relevant formulas, and provide a demonstration of an experiment that we will be using. We will also show you how to analyze the data. The experiment in this video will be extraordinarily helpful for you to visualize the relationships between these principles. Linear acceleration measures the change in velocity over time and is expressed in units of meters per second squared. Similarly, angular acceleration measures the acceleration of a rotating object and is expressed in units of radians per second squared. Torque is defined as the product of the force F applied on a lever arm, the distance or radius r from the point of application to the pivot point, then multiplied by the sine of angle theta between the force and the lever arm. However, since all the forces are perpendicular to the lever arm, sine theta will always be equal to 1, so we can reduce this equation to just force times radius. In this experiment, we will vary the torque applied to a rotating system by adjusting the weight of a falling mass, which causes a pulley to rotate. The angular acceleration of the rotating system will be measured using a phone attached to the rotating pulley, allowing us to determine whether there is a proportional correlation between net torque and angular acceleration. To calculate angular acceleration, we will find the slope of a graph that represents the changing velocity over time. By calculating the change in velocity over the corresponding change in time, we can determine the angular acceleration of the system. We will go into detail on how to do this later in the video. To calculate net torque, we will apply several kinematic principles. First, we will use the formula d equals v initial t plus 1/2 at squared to calculate the acceleration of the falling mass. From this acceleration, we can apply the formula F net equals ma to derive the force of tension in the system, considering the mass, acceleration, and neglecting friction forces. As shown in this diagram, the force on the top pulley is the same as the tension force on the string. By subtracting the force of tension from the force of gravity, we obtain the downward force that generates torque on the system. Torque is then calculated using the same equation as earlier, F times r, where r represents the radius of the pulley. In this experiment, we will be using a pulley with a clamp, string, weights of different masses, and a phone with the Phyphox app. Additionally, we used tape and glue to attach everything together. Connex pieces were also attached to the pulley to stabilize the phone. Set up your experiment with the string wrapped around the top pulley and the phone attached to this pulley. First, hook the weight you are using around the string here. Make sure that the string is tightly wound around the top pulley, otherwise your measurements may not be accurate. Ensure that your phone is securely attached to the pulley. If it isn't, that's bad. Open Phyphox gyroscope. You may also wish to enable remote access, which will allow you to control and use Phyphox from another device, such as your laptop. Start the Phyphox gyroscope, then let the weight fall. This will cause the top pulley to spin, while the Phyphox gyroscope measures the angular velocity. Take this data and export it to Excel. Repeat this experiment with the same mass, then repeat it using a different mass. After downloading your data, rename the Excel file so that your data is organized. Then open each file and drag the sheet containing the data to the same file. Select the time and absolute columns, then use a scatter plot to graph them. You will see that the velocity increases at a steady rate until a certain point, then it decreases. The angular acceleration can be calculated by finding the slope of the increasing part. To do this, find the point where the velocity is about 1 radian per second and the point right before it starts to decrease. The slope between these 2 points is the angular acceleration. Do this for each sheet, then compare the angular accelerations of the different masses. After finding the angular accelerations of all your trials, find the average angular acceleration for each mass as well as the error margin. To show the results of each trial for each mass, you can create bar graphs with an average line and error bars. To calculate the torque acting on the top pulley, use the formulas that we discussed earlier. As shown in the diagrams, the force acting on the pulley is equal to the tension of the string when a mass is attached. Plot your experimental points with a trend line and error bars. To confirm or disprove the hypothesis that torque is proportional to angular acceleration, check whether or not the experimental data matches the expected outcomes. Create a theoretical line by taking your first data point and extrapolating what the expected results would be for the other torques. As you can see in our experiment, 2 of our experimental points align closely with our theoretical line, falling within the error bars. However, we must acknowledge that one of our data points lies outside the theoretical line. This discrepancy can be attributed to the fact that one of our recordings used to measure the displacement of the falling mass was unable to provide an accurate measurement, leading to an improper calculation of torque. Despite this anomaly, considering the overall trend, we can still draw the conclusion that torque is somewhat proportional to angular acceleration. This experiment on angular acceleration and net torque is easy to conduct, requiring minimal equipment and time. It is ideal for demonstrating rotational dynamics in a high school setting. By adjusting weights to change the torque on a pulley system and utilizing a gyroscope on a smartphone to measure angular acceleration, students can confirm the proportional relationship between torque and angular acceleration. Additionally, it opens up avenues for further investigations, such as studying the impact of rotational inertia by adding weights to the rotating object, or investigating the effect of changing the pulley's radius.